Okay, sorry for starting late. Today I wanted to go through the solutions. So this is from a different class. Sorry. Today I wanted to go through the solutions to the exam. Let's see. Also, I kind of want to, this week, I hope to finish cardinality. I want to talk about countable versus uncountable. What do those things mean? Definitely we should always in a set, I think, in a set theory class, we should prove that the real numbers are uncountable, among other things. And this will kind of lead us into cardinal arithmetic, at least the basics or something. Okay, and then looking towards, so that's like today's or maybe later this week, especially this, maybe later this week. Okay, but that will lead us into, next week, next few weeks, we'll talk about the axiom of choice. This is kind of like one of our axioms that we take for set theory, but it's kind of like the odd one out. But we'll see why later. And then the last topic is just a quick overview. Well, just so quick for topology. Just so you know what's coming up. Okay, so let's work on the solutions to the first exam. So we had question 1. There are several different ways to do this question. I'll just present one possible thing. If you did it a different way, it doesn't mean that you're wrong. You have to show and then prove this for all natural numbers. Okay, sorry about that. Okay, right, so this is question 1. So one thing to notice is that, so we want to prove that these two sets are equal. Since the definition of m less than n implies that m is an element of n, this so all the natural numbers that are elements of n is automatically a subset of n. Okay, so really we have to show that every element of n is an element of this side. Well, an element of n satisfies if you're an element of n, you're less than n. Well, as long as, so essentially what we can say is that if we know that all the elements of this are natural numbers, then we're done. Okay, so there's like multiple ways. I'll give you at least, I mean, there's more than this even, but here's two ways to go. One is show for all n is a subset of the natural numbers. 2, show that basically directly show this directly by induction. Okay, and I think there's more ways, like, but I won't get in. I mean, that's fine. Okay, so I haven't looked to see what is the more popular way, but either one of these is fine, or a different way. Let's do it this way. You know, sometimes you don't always do things the quickest way. Okay, so right, so let's do this. Okay, P of n is just going to be the statement that n equals less than n. Okay, so we proceed by induction. So base case n equals 0. Well, in this case, n is the empty set, and the set of natural numbers that are less than 0 is also the empty set. They're both the empty set. Okay, now assume that for some natural number n equals the set of all natural numbers less than n, is like, this is always, so it's clear that all the natural numbers less than n plus 1 is a subset of n plus 1. Okay, now we have to let, okay, so let x be an n plus 1 union singleton of n. Okay, so either x is an element of n or x equals n. X equals n. Well, our assumption is that n is a natural number, so x is a natural number. And also, by assumption, x is an element. So x is in this set. Okay, the other. Okay, but our induction hypothesis says that induction hypothesis so we're in the case that x is, right, just the definition of less than. So x is less than n plus 1. X is a natural number. Okay, because of our induction hypothesis. Just a minute. Okay. So therefore, x is a natural number is less than n plus 1. Okay, so therefore, we've shown that n plus 1 is the set of all natural numbers less than n plus 1. Okay, so therefore, P of n plus 1. So by induction, P of n holds for all n. That's for all. That's the first question. Okay. Now for the second question. The second question wasn't supposed to be a trick or anything. You know, you can do it like kind of in a direct fashion. Is what's it called? De Morgan's law, or whatever you want to do. We're supposed to prove. We're supposed to prove A minus B and intersect B are sets, and then prove like this thing like De Morgan's law. Okay, solution. Well, let's prove that. Well, the definition of A minus B is all the elements of X in A, all the elements of A that are not in B. This is a set by the axiom scheme of comprehension. our property is that X is not in B. And our set that we. Okay, what about A intersect B? You can look at this as a set of elements schema of comprehension. Again, our property is that X is in B, and our set is. I guess there would be more to do if I had asked you to like prove that A minus B is like, you know, does it define, is there a unique set satisfying this thing? And then you'd have to use like the axiom of extension and all that. But I didn't really ask that, so it wouldn't require you to do that. Okay, so I was just looking for you to say like, use the axiom of comprehension or something like that. Now we want to show like these two sets are the same. We have to show that A minus B union C equals A minus B intersect A minus C. Well, let X be in A minus B union C. So X is in A, X is not in B union C. Well, X is not in B or C either. X is not in B. Oh no. How should we go about this? I guess we can break it up into cases like, oh wait, no, we should do it a different way. We should suppose X is in B. Well, then X is in B union C. This is a contradiction. So X is not in B. X is not in B, and similarly, X is not in C. And so since X is in A, but not in B, X is in A minus B, A minus C, so therefore X is in intersection. Okay, and then we just do, this shows that every element of this is an element of that. Now suppose we have something in the other direction. Okay, then X is in A minus B, X is in A minus C. So X is not in C. Now, if X were in B union C, it would be in either B or C. So if it were in, we can say otherwise, X in B or X is in C, both of which are false. Okay, so X is not in the union, therefore X is in A minus B union C. And if you wanted to put a much shorter proof using Morgan's laws, that's fine by me. Anyways, okay, oh yeah, and then we should say like, therefore by axiom of extension, these two sets are the same. As required. Now we can put in a little square. Okay. And now we move on to question 3. F is 1 to 1. A and B are sets. Well, N is, I don't know. Again, F is 1 to 1. A and B are sets. We're showing that F of A minus B is the same as F of A minus F of B. And then I wanted to, and then I asked you, is this still true if F is not 1 to 1? And if at some point during your proof you use the fact that F is 1 to 1, then you would probably answer that it's not true if F is not 1 to 1. That's what I was looking for. Okay. It is okay. Okay, so let's remind ourselves of what these definitions are. F of A minus B, well, that is the set of all things like F of X, where X is in A minus B. And F of A minus F of B is the set of all Y's, I guess, such that Y equals F of X for some X in A, but Y is not equal to F of, X prime for all X prime, well, X prime in B. Or in other words, Y is not in F of B. Okay, so, we just let Y be in one side and try to prove this on the other side, and then vice versa. Okay, so let Y be in F of A minus B. Okay, well then you can write Y equals F of X. Okay. Okay, now what could happen is that, sure, X is in A, but not in B, but Y could be equal to F of X prime, and then X prime might be in B, So that doesn't happen if F is 1 to 1. So that's where the 1 to 1-ness comes in proving that Y is not an element of F of B. So X is in A, so Y equals F of X is in F of A. Okay, now suppose for a contradiction that Y is not in F of B, or suppose that Y is in F of B. And write, again, this is to obtain a contradiction, write Y equals F of X prime, some X prime in B. Now, F of X equals F of X prime. Since F is 1 to 1, here's where we use that F is 1 to 1. Okay, therefore, X, which is X prime, is in B. That's a contradiction since X is in A minus B. Okay, well, that means that our contradiction is to this fact that Y was in F of B. So Y is not in F of B. That establishes that Y is in F of A minus F of B. And this establishes, so far we've shown that f of a minus b is a subset of f of a minus f of b. And we had to use the fact that f was 1 to 1 to prove this. Okay, now let y be in f of a minus f of b. Then y equals f of x. The sum x in a. If x is in b, then y is in, then f of x is in f of b, which is not what we like, the opposite of what we assumed. So this establishes that x is not in b. So therefore, x is in a minus b. Therefore, y is in f of a minus b. So this tells you that f of a minus b is, or sorry, f of a minus f of b is a subset of this. Okay. And now we've shown they're both subsets of each other, so they're both equal. That's the end. And you can say like by axiom of extension or something. Okay. The last question, another induction question. Question 4. Just prove for all natural numbers that are not equal to 0, there exists natural number k with k equal, or sorry, with n equals k plus 1. Proof P of n is just going to be either n equals 0 or n is equal to k plus 1 for some k. Okay, our base case is that if n equals 0, it's trivial, right? That's one of the P of n. The base case, P of 0 is true. Because n equals 0 is one of the defining things for P of n. Okay, now assume P of n for some natural number. And then to prove P of n plus 1, we don't actually even use the assumption of P of n, but that's okay. It's induction step. Well, n plus 1, we have to show n plus 1 is equal to k plus 1 for some k. Well, n plus 1 is just n plus 1. So we're taking k to be n. This proves P of n plus 1. So P of n plus 1 is just trivial. Okay, so by induction, P of n holds for all n. In other words, every natural number is either equal to 0 or of the form k plus 1. And that's just a way to rewrite the thing in the question. Okay, and oh yeah, so I guess we should rewrite that. So n equals 0 or n equals k plus 1 for all n. Well, there's like some missing quantifiers there, like, or there exists k such that n equals k plus 1 is really what I should write there. Okay. So that is it for the solutions. Let us just take a break until 3:40. And then when we come back, we're talking about cardinality. Okay, so I'll try and get back in that mode. Okay. Okay, so see you guys in 7 minutes.